Welcome to Real Chemistry. Today we're going to be talking about partial pressures. The idea here is that we can think about the pressure of gas, the force it exerts every single time a gas molecule bounces off of you, as the sum of all the different gases in a mixture. Let me explain. So right now, the atmosphere is exerting a force on you. And it turns out that the atmosphere is made up of mostly oxygen and nitrogen. And that oxygen exerts a force on you every time it collides with you. And same with the nitrogen. And if you want to know the total pressure that results from both of those gases, it turns out you can just add them up. And so that's this equation down here below. It tells us that we can take the pressure from oxygen and the pressure from nitrogen and just add them up, and that'll give us our total pressure. This is called Dalton's law of partial pressure. Let me show you another diagram that might help make this a little clearer. So here we've rewritten our equation just in terms of P with a little t, that stands for pressure total, P with O2, that stands for the pressure of oxygen, and P into the pressure of nitrogen. And we can think about a box that contains just our oxygen or just our nitrogen or both of them mixed together. And if we had a box with just oxygen, let's say oxygen are these blue spheres bouncing around. If we had a box with just oxygen, its pressure might be 159 millimeters of mercury. Now let's say we have another box filled with nitrogen, and these are yellow spheres, and every single time those spheres bounce off a wall, they exert a force, and that force results in a pressure. And the pressure from all of those different nitrogen atoms is 593 millimeters of mercury. If we put all of the nitrogen spheres together with all of the oxygen spheres so that they're all bouncing around in the same box, we can figure out the new pressure just by adding them together. So if we mix together those oxygen and nitrogens, we'll get the sum of those two pressures, 752 millimeters of mercury. So it turns out we can just add up the contributions from pressures from different gases and get the total overall pressure. We can also, it turns out, rewrite the ideal gas law. So let's say that you have the partial pressure of nitrogen. That is the pressure due just to those nitrogen spheres. Well, you can actually calculate how many moles of nitrogen you have using the ideal gas law. You can see here that we've just rewritten the ideal gas law, and we've added a little N2 here, and that tells us that we're taking the partial pressure, the pressure that comes from just nitrogen, and that if we multiply that by the volume, that'll give us the moles of just N2. Similarly, if we start with the partial pressure of oxygen, that's just the pressure that comes from oxygen, we can calculate just the moles of oxygen. So we can use partial pressures, the fact that we can split up the contributions of pressure, to rewrite the ideal gas law. And we can solve a bunch of different chemistry problems using these new equations. So let's take a look at a type of chemistry problem you might see that uses these partial pressure equations. So this question says a mixture of argon and oxygen has a total pressure of 1.3 atm. The partial pressure of oxygen is 0.2 atm. And the question asks, how many moles of argon are present in 1.3 liters at 325 Kelvin? So a ton of information there. And partial pressure problems involve a lot more variables than we've probably dealt with up to this point in your chemistry class. So how are we going to solve this problem? It's important that we break it down piece by piece, and it really starts to be important here that we write down each of the variables that we're given and also each of the variables we want to find. So as we read through the problem, we're told that there's a mixture of argon and of oxygen. So this is telling us that we have a box with gas in it, and it's just argon and oxygen. And we're told that there's a total pressure of 1.3 atm. And that's a good key right there that we're going to be using our partial pressure equations. Anytime they talk about mixtures of gases and total pressure, we're probably going to be using our partial pressure equations. And it also tells us the partial pressure of oxygen, the volume, and the temperature. And so what we're going to do in our first step is we're just going to identify the variables and our unknowns. And so we've been told that we have a mixture of gas and that the total pressure is 1.3 atm. So the first thing we'll write down is that our total pressure is 1.3 atm. As we keep reading, we see that we have a partial pressure of oxygen given, and that it's 0.2 atm. And so that means I can write P with a little O2 down there, and that stands for the partial pressure of oxygen, the pressure that comes just from oxygen. And that has a pressure of 0.2 atm. The other things we're given is the volume, which is 1.3 liters. And we're also given the temperature, which is 325 Kelvin. And what we're asked for is the moles of argon. And I'm going to go ahead and write that as N with a little AR below it. And we don't know that. So all I've done is I've taken what we've written in the problem and rewritten what we know and what we're looking for. And now we're going to go take a look at our partial pressure equations. Well, here's what we want to find out. We know that eventually we want to get to moles of argon. So we want to find this guy. And if we want to do that, let's take a look at what we need. We need temperature, which we have. We need the gas constant, which we have. So we're good on those two variables. We need the volume, which we have. And we also need the pressure of argon. We don't have that. So let's list that as another unknown. If we can find the partial pressure of argon, then we can just use that ideal gas law to solve for the moles. So that's another thing we don't have that we'd like, the partial pressure of argon. And now we can see that if I go ahead and take a look at my other equation about the total pressure, that I can actually solve for the pressure of argon. How is that? Well, this total pressure equation, which just tells me that I can add up as many gases as I have. That's why there's A, B, and C. It's just saying if you have 3 gases, you can add them up. And then it goes dot, 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 because it's saying this dot, dot, dot right here is saying if you have more gases, you can just keep adding them up. In this case, we just have 2 gases, oxygen and argon, which means we can rewrite our equation as the total pressure is equal to the pressure from oxygen plus the pressure from argon. So that's the equation for our total pressure because we just have those 2 gases, oxygen and argon. And now if I want to solve for the partial pressure of argon, all I have to do is subtract the pressure of oxygen from both sides. And when I do that, I'll get that the pressure total minus the pressure from oxygen is equal to the pressure from argon. As we'd expect, because we just have 2 gases. And so then I plug in my pressure total, which is 1.3 atms, and I subtract my pressure from oxygen, which is 0.2 atms. And I'm going to get out my pressure from argon, or 1.1 atms. So now I've solved for my pressure from argon, and it's 1.1 atms. And that's really helpful because now I can go back and I can say, oh, when I was looking at my ideal gas law equation, I noticed that I had everything I needed to solve for my moles, right? I wanted this moles right here, and I didn't have that, but I did have my temperature, my gas constant, and my volume, and now I have my pressure for argon. So I can erase that question mark. I have that now. And so now I can use that ideal gas law equation to solve for moles. And that's what I'll do right here. So we know that if I have the partial pressure of argon, and I multiply that times the volume, that'll give me my moles of argon times the gas constant times temperature. And the temperature, remember, is in Kelvin. So what I need to do here to solve for moles of argon is divide both sides by RT. And when I do that, those RTs there will cancel, and I'll be left with my equation for moles, which tells me that the moles of argon is equal to the partial pressure of argon times the volume divided by R times T. And now I'm all set to just plug in my numbers. The partial pressure of argon is what I just calculated. It's 1.1 atm. And my volume, which I wrote down way back over here, is 1.3 liters. And then I divide that all by my gas constant, which is 0.082057. And I multiply that by my temperature, which is 325 Kelvin. So when I plug that all into my calculator, I will get out 0.054 moles of argon. And that's my final answer. So, because I was given the total pressure and how much of that pressure came from oxygen, I could calculate how much of the pressure came from argon, and then how many moles there was of argon. A couple things to note about this problem. One is that the units just were in the nice form from the beginning, so I didn't have to do any unit conversions. The pressure was in ATM, which is what I need for that gas constant I used. The volume was in liters, which is what I need. And the temperature was in Kelvin. But it's very common to have to do temperature conversions throughout these problems also. Another point to make is that it's really common to ask for mass instead of moles. But remember, if you're ever asked for the mass of argon instead of the moles of argon, it's just one more step. Just make sure when you're reading the problem, you always read mass and moles as sort of interchangeable. It's very easy to go between mass and moles. So that's one example of a partial pressure problem. As you can see, they can be pretty lengthy. If you'd like to see another example of a partial pressure problem, check out my other video, Partial Pressures Practice Problem. If you have any questions, please leave them below. As always, subscribe to receive updates about future chemistry videos.